Understanding of system design is very important when you want to grow from software engineer to become a software architect or a solution architect. System design is not coding at scale, but we can say it's thinking in scale. And it means that we need to design our app such that they last longer. To do same, we need to understand the concept of sharding, queues, gap theorem, etc., which we'll be discussing in these videos. The topics discussed in these videos are high availability and role of load balancers, gap theorem, where we'll be discussing consistency and partition tolerance. Then we'll be using CDN, Content Delivery Network, DNS, domain name system. Next, we will understand what is database sharding, scaling. We'll also see what is rate limiting and what is distributed messaging queues. And finally, we'll go through what is disaster recovery and monitoring. So let's go through them one by one. High availability or HA means that designing systems that are always on, accessible 24 by 7 with minimal downtime, no matter what happens behind the scenes. Whether it's a server crash, a power outage, or a network failure, a highly available system keeps running. The core idea of HA is resilience. It's not about preventing every failure, it's about making sure your system can withstand failures gracefully. That's why HA setup often spans multiple data centers, regions, or availability zones. If one site goes down, traffic is automatically rerouted to another, with users none the wiser. Redundancy is the secret sauce here. Multiple copies of everything from servers and database to network path ensures that if one component fails, another runs. Immediate takeover. This often is done with load balancers, automated failovers mechanism, and real-time backups that ensures data and services stay available. Most HA systems also rely on health check to monitor services and detect problem in real time. When something isn't working right, it's isolated and replaced quickly before it's affect user experience. HA is specifically critical for mission critical applications like banking platforms, e-commerce websites, healthcare systems, or emergency response apps. These can't afford downtime, not even for a minute. Think of high availability as an airplane with multiple engines. Even if one engine fails mid-flight, the plane keeps going. That's the mindset we want for any system users depending on. Cloud providers like AWS, Azure, Google Cloud for infrastructure and services level agreement or SLAs, promising high level uptime, often 99.99% or more, based on well architected HA designs. Ultimately, high availability is about trust. Users don't care how complex your architecture is, they just expect your app to work always. And HA is what makes possible, even when things go wrong behind the scenes. Together with this, we also need to understand the role of load balancers here. In modern web architecture, load balancers are essential for keeping systems fast, reliable, and scalable. Their job is to distribute incoming traffic across multiple servers, making sure no single server gets overwhelmed. Without them, a surge in user requests could bring your entire system to its knees. By placing the load, these tools dynamically improve performance, reliability, and overall scalability. Whether it's a sudden spike during a product launch or steady growth over time, a load balancer ensures everything runs smoothly behind the scenes. There are four different types of load balancers depending on the layers they operate on. Layer 4 load balancers work at the transport level, handling traffic based on IP address and TCP UDP ports. Layer 7 load balancers operate at the application level, managing traffic based on things like URL, cookies, and headers, which are great for smart routing decisions like redirecting an API traffic to one group of servers and media to another. Most load balancers also perform health check. If a server goes down or becomes unresponsive, The load balancer simply routes around it. No downtime for users. Many also support features like sticky sessions, that is keeping users on the same servers, SSL termination, which is offloading the encryption, and path-based routing for advanced flexibility. There are hardware applications, software-based solutions like HA Proxy and Nginx, and cloud native services like AWS Elastic Load Balancer ELB, Azure Load Balancer, or Google Cloud Load Balancing. One of the most powerful aspects of load balancers is how they enable horizontal scaling. By abstracting backend servers, you can add or remove instances on the fly without user noticing. It's like having a traffic cop at busy intersection, redirecting cars efficiently to avoid jams and accidents. At scale, no system can survive without a solid load balancing strategy. It is not just a performance booster, it is a critical safety net for modern infrastructure. Now we'll see what is consistency in CAP theorem. So on the image, we can see this is the CAP theorem, where we have consistency, availability, and partition tolerance. Consistency is the fundamental property in system design. It ensures that every user sees the same up-to-date data, no matter where and how they access it. In the world of distributed system, it plays critical role of maintaining trust and correctness. It's one of the three pillars of CAP theorem: consistency, availability, and partition tolerance. You can only fulfill guarantee two of the three at a given moment. So when a network partition happens, system often have to choose either stay available or stay consistent. In a consistent system, once data is written or updated, every read by every user or service returns the latest result. This is called consistency. There is no confusion, no conflicting states. Think of a banking app. If you transfer 500, you expect new balance to reflect immediately. Any delay or inconsistency could erode trust. This is called strong consistency. It avoids problems like double spending, or conflicting updates. However, achieving strong consistency, especially across geographically distributed systems, can introduce latency. The system may need to coordinate across multiple nodes before confirming an action, slowing down responses to ensure everything stays synchronized. In some systems, like traditional relational databases, RDBMS, they're designed for strong consistency. Other like NoSQL may opt for eventual consistency, where updates propagate over time. This approach keeps systems available even during the network failures, but comes with trade-offs. Choosing consistency versus availability often depends on your business requirement. For financial systems, accuracy and correctness are critical, so consistency wins. For social feeds, for shopping carts, etc., speed and uptime might matter more, so eventual consistency could be acceptable. Consistency ensures reliability, trust, and predictability in your application. It's what allows users and your system to operate with confidence in the data what they see. Together with this, we also need to understand what is partition tolerance. Partition tolerance is a foundational concept in distributed system. It means your system can continue operating even when parts of the network can't communicate with each other. Imagine your infrastructure spread across regions or data centers. Now picture a network issue that can cause some nodes to lose contact. That's called a network partition. In a partition tolerant system, the application doesn't freeze or fail. Instead, it adapts. It might queue messages, delay writes, or let parts of the system keep working independently until communication is restored. It's about resilience and not performance. Partition tolerance is on one side of the well-known CAP theorem, which says in any distributed system, you can only fully guarantee two out of three: consistency, availability, and partition tolerance. In today's cloud-based world, partition tolerance is usually non-negotiable because network failures, no matter how rare, will happen. Think of chat app. If you're offline, it still lets you write messages and queues them up. Once you're reconnected, everything syncs, your messages go through. Systems like Apache Kafka, Cassandra, Amazon DynamoDB, etc. are architected with principle in mind. They ensure that when networks split, the system doesn't break in bits. Partition tolerance doesn't mean everything runs perfectly. It means things keep running. There may be delays or traffic offs in consistency, but the goal is avoid total failure. In cloud native, geographically distributed system, partition tolerant isn't just nice to have, it's essential. Because in chaotic, unpredictable internet, your system has to survive the storm. And that's exactly where partition tolerance is built for. Next concept is content delivery network. A CDN or a content delivery network is one of the most powerful tools for speeding up and securing your web application. At its core, CDN catches content closer to users geographically, storing copies of static assets like images, videos, JavaScript files, and style sheets on edge servers around the world. So when someone visits your site, instead of pulling everything from your central server, their request is routed to nearest CDN node. This means faster load time, lower latency, and a more reliable experience no matter where the user is located. CDNs do more than just improve speed. By handling a huge chunk of your traffic, they offload the burden from your original servers, making your system more scalable. They are specifically valuable during traffic spikes. Think product launches, flash sales, or vital moments when server load can skyrocket unexpectedly. Many modern CDNs also come with built-in features like DDoS protection, rate limiting, and HTTPS termination, giving you an extra layer of security and performance optimization without extra infrastructure. Popular CDN providers include Cloudflare, Akamai, Fastly, and AWS CloudFront, each offering global network with fine-tuned controls for caching, routing, and access management. CDNs are essential for modern web, e-commerce sites, SaaS platform, and streaming services, where performance directly impacts engagement and revenue. The next component is DNS, domain name system. DNS or domain name system is often called Internet's phone book, and for good reason. It translates human-friendly domain name such as google.com, facebook.com, yahoo.com into machine-friendly IP address, which we can see in the screen. So our browser knows where to send the request. Without DNS, we'd all have to remember strings of number just to visit a website. Thanks to DNS, we can just type a name and it figures out the rest. Behind the scene, DNS is hierarchical. It sends at the router servers and works in the way down through top level domains like .com, all the way to the authoritative name servers managed by your registrar or DNS provider. To keep things fast, DNS relies heavily on caching. Your computer, browser, ISP, and even DNS resolver store previous lookups to avoid repeating the same queries. It boosts performance and reduces latency. But DNS isn't just convenience, it's critical to system availability. If your DNS fails, user won't reach your site, even if your servers are running perfectly. That's why having a redundant DNS providers, failover records, and health check endpoint is also important for resilience. Modern services like AWS Route 53, Cloudflare DNS, and Google Cloud DNS offers global coverage, fast response time, and features like geo-routing and DDoS protection to keep your services reachable and responsive. Think of DNS as a first step in every internet request, whether it's loading a website, calling an API, or accessing cloud resource. It all begins with DNS, and when it fails, everything else grinds to halt. So while it may seem invisible, DNS is one of the most critical and foundational layer of the internet, and your system's reliability depends on getting it right. The next concept is database sharding. As our app scales and data explodes, sharding becomes a powerful technique to keep performance high and system responsive. Simply put, sharding splits your database into smaller, more manageable pieces known as shards. As you can see on the screen, each shard holds a subset of total data, often based on something like user ID, region, or account type. This division dramatically improves performance and scalability, especially when dealing with millions or billions of records. Instead of overloading one massive database server, sharding spreads the load across multiple servers or clusters, reducing contention and making read and write operation much faster. Each shard can be hosted on different machines or even across geographical regions, giving you the flexibility to scale horizontally and handle more traffic without a single point of failure. That's why you'll need sharding in action behind massive scale platforms like social media networks, e commerce giants, and streaming services. However, with great power comes great responsibility. One big challenge is managing cross shards queries efficiently. When data lives in separate places, things like join, aggregate, backups, and even data consistency require careful planning and architecture. Sharding isn't just bolt on the feature, it's often backed into the core design of system like MongoDB, Elasticsearch, and Apache Cassandra, where high scalability is non-negotiable. Think of sharding like dividing a giant encyclopedia into chapters and storing each chapter in a different library. It's faster and more efficient to search a specific topic in one volume than to flip through the thousands of pages in a single book. In high growth, data heavy application, sharding isn't optional. It's essential to keep systems fast, resilient, and ready for the future. And the next concept which we need to understand is horizontal and vertical scaling. Scaling is how you system handles increased traffic or load, and it's one of the most important concepts in building resilient, high performing applications. Whether you are dealing with a surge of users, data, or requests, scaling ensures your app doesn't slow down or crash under pressure. There are two types of it, vertical and horizontal scaling, which we can see on the screen. Vertical scaling means upgrading a single server, adding more CPU, RAM, or faster storage to handle the increase in demand. It's simpler to implement, especially early on, but eventually we hit the hard limits. There is so much we can add to one machine, for example, as RAM or CPU. On the other hand, horizontal scaling means adding more servers, distributing the load across multiple machines. This approach is more complex to architect, but offers far greater long term scalability and resilience. If one server fails, another can pick up the stack, which adds redundancy. Modern cloud applications like AWS, Azure, Google Cloud make horizontal scaling much easier with features like auto scaling groups, which automatically adjust the number of instances based on the demand. This means your infrastructure can scale up during peak hours and scale down to save cost when traffic drops. One key enabler of horizontal scaling is designing stateless application. When an app doesn't rely on local state, any server can handle any request, making it much easier to distribute the load across machines. You can think of vertical scaling as buying a stronger, more powerful machine, while horizontal scaling is hiring more machines to work together as a team. Both have their place, but for most large scale modern systems, horizontal scaling wins out, offering better flexibility, redundancy, and future proofing. In today's cloud native world, understanding when and how to scale is essential to build a system that grows with users without missing a beat. Related to this, we having one more concept called rate limiting. Rate limiting is a technique used to control how many requests users or servers can make with a specific time frame. It plays a crucial role in protecting APIs and servers from being overwhelmed, whether due to malicious activity or unintentional overuse. This mechanism is essential for defending system against abuse such as spam, DDoS attack, accidental infinite loops in code. By setting boundaries on how often a resource can be accessed, rate limiting ensures both stability and security. There are several common rate limiting strategies such as fixed window, sliding window, and token bucket algorithm. Each approach balances flexibility, fairness, and system efficiency in different ways. When limits are exceeded, users often encounter a 429 or too many request error. This response tells him to wait before making more requests, helping to regulate traffic without crashing the system. A rate limit can also be applied at different levels, such as at user level, per IP level, per API key. This allows developers to fine tune control based on use case and expected traffic. By enforcing these limits, system can maintain consistent performance and ensure fair usage across the users. Most major platforms like Twitter, Stripe, GitHub implement some or other form of rate limiting. You can enforce rate limiting directly in application logic or via API gateways, which offers central control and scalability. Think of rate limiting as like a bouncer at a nightclub, allowing only a certain number of people in at a time to keep things safe and orderly. It's a simple concept, but critical for keeping modern web systems running smoothly. Next concept is distributed messaging queues. In today's world of distributed system and microservices, a messaging queue is a fundamental building block. It allows services to communicate asynchronously, meaning they don't need to talk to each other in real time. Instead of one service calling another service directly and waiting for a response, it sends a message to a queue. That message just sits there until the receiving service, often called a consumer, is ready to process it. This pattern is powerful because it decouples your services. One service can keep moving forward without waiting on another, which makes the system more resilient and easier to scale. It's especially useful in scenarios like order processing, background task scheduling, log aggregation, notification, etc. Messaging queues also support useful features like retries in case something fails, delays to schedule work in a future, and back pressure to slow down traffic when systems are overloaded. These capabilities help keep everything running smoothly even under heavy load. Popular technologies in this space include Apache Kafka, RabbitMQ, Meson SQS, each with its own strength and use case. At the core, you will find these three main roles: producers, which send messages, consumers, which receive messages and process them, and brokers, which manage the flow and delivery of message, as we can see on the screen. Some systems also support publish or subscribe or pub sub models where messages are published to a topic and multiple subscribe and consume them independently. Perfect for things like real-time analytics or multi-user notifications. Messaging queues are the circulatory system of modern microservice architecture. They move information efficiently, keeping components loosely coupled and make your system more robust and scalable. Next concept that we have to understand is disaster recovery. Disaster recovery or DR in your organization's plan for when things go wrong, really wrong. Imagine the worst case scenarios: fire destroys data centers, flood disabling physical infrastructure, ransomware locking your systems, or even entire cloud regions going offline. DR is how you prepare for these moments so your business can survive and recover quickly. At the heart of a good DR strategy are the key components like reliable backups, failover systems, and clearly documented runbooks. Backups should be frequent, thoroughly tested, and stored safely, including offline or in geographical separate location. You don't want to find out a backup it's corrupted after you need it. Two critical metrics to guide your DR planning: recovery point objective RPO, which defines how much data you can afford to lose, and recovery time objective or RTO, which is how fast you need to be up and running again. These help you make smart choices about what technologies and processes to invest in. Some companies maintain hot standby environments that are always ready to take over. Others use cold or warm standby servers, spinning up new infrastructure only when disaster strikes. In the cloud, many organizations take advantage of multi-region deployment strategies to build resilience and avoid single point of failures. But DR isn't just technical checklist, it's a human one too. Your teams need to know their role, communication channels must be clear, and everything should be trained and ready to act fast. A well placed DR plan means the difference between a minor hiccup and a major catastrophe. Think of disaster recovery like a seatbelt. You might not need it every day, but in critical moment, it can save your data, your systems, and your business. The last concept that we have to understand is monitoring. Monitoring is the heartbeat of any modern digital system. It continuously tracks the health and performance of your infrastructure, applications, and services in real time. From CPU usage, memory consumption, response latency, to error rates, request volumes, and traffic patterns. Monitoring gives us eyes on everything that matters. The true power of monitoring is in early detection. It helps you to catch issues before users even notice something is wrong. Is a service slowing down? Is traffic spiking unexpectedly? Are error rates creeping up? Monitoring tools keep watch and immediately trigger alerts when defined thresholds are breached. So you and your team can act fast. To make sense of all this data, monitoring platforms offer dashboards, visual interfaces that also shows what is happening behind the scenes. These dashboards are critical for day-to-day operations, capacity planning, and post-incident reviews. But monitoring is just one piece of bigger picture called observability, which includes logs, traces, and metrics. Logs tell you what happens, traces show how requests flow through your system, and metrics qualify it all. Together, they help you fully understand not just what went wrong, but why. Popular tools like Prometheus, Grafana, Datadog make all this possible. They gather data, analyze it, and present it in a way that helps you to respond to incidents quickly and maintain high reliability. Think of monitoring like a vitals monitor in a hospital. Most of the time, it's quiet. But the moment something spikes or drops, it sounds the alarm, giving you a chance to intervene before it's too late. In today's world of complex, fast-moving systems, no infrastructure is completely complete without robust monitoring. It's not just the best practice, it's a survival necessity. So these are the 12 most important concepts of system design. And based on this, we can say that our app is well architected. That's all in this video. Thanks.